A colossal explosion may have just rocked the center of our galaxy, and scientists think it happened recently. Are we witnessing the Milky Way waking up? Astronomers have discovered cold hydrogen clouds inside the Milky Way's scorching Fermi bubbles, something once thought impossible. This finding hints that the explosion behind the bubbles, likely from our galaxy's central black hole, may have happened more recently than believed. It's a game-changer for how we understand galactic evolution and black hole activity. In this video, we'll break down the discovery, how it was observed, and what it means for our understanding of galaxy evolution and black hole activity. The Fermi bubbles are vast lobes of high-energy plasma extending above and below the galactic center. First identified in 2010 using NASA's Fermi Gamma-Ray Space Telescope, they're invisible in visible light, but glow in gamma-ray and X-ray observations. They're believed to be the result of a large-scale release of energy from the galaxy's core, possibly jets or outflows driven by Sagittarius A** millions of years ago. Until now, these bubbles were understood primarily as regions dominated by extremely hot plasma. That's why the discovery of cold hydrogen clouds inside them is so unexpected. Led by Rangman Bordeloi at North Carolina State University, researchers used the Green Bank telescope to detect these cold clouds measuring between 13 and 91 light-years across. They were found about 13,000 light-years above the galactic plane, well within the northern bubble. This hydrogen is cold in a relative sense, around 10,000 K, much lower than the surrounding million-degree plasma. Under normal conditions, clouds like this would be unstable or short-lived in such an extreme environment. The fact that they're still present suggests they were likely swept into the bubbles during the event that formed them, not formed afterward. Given how long they've lasted, this provides a constraint on when that eruption occurred. If these clouds are slowly eroding due to their surroundings, and current models suggest they should, then they must have been injected into the bubbles relatively recently. Otherwise, they'd no longer be visible. This discovery acts like a cosmic clock, suggesting the bubbles formed just 6 to 9 million years ago, far younger than once thought. It also shows that even in extreme regions, cold gas can survive, reshaping how we understand energy and matter flow in our galaxy. The most immediate consequence of this discovery is that it tightens the estimated timeline for the Milky Way's last significant central outburst. Many prior models placed the bubble's formation somewhere between 10 and 30 million years ago, but the survival of cold hydrogen gas sets a much shorter window, less than 10 million years, and potentially much closer to 5 or 6. This may seem minor, but it's significant in galactic terms. It implies that Sagittarius A*, a black hole currently classified as quiet or inactive, was erupting not so long ago, astronomically speaking. This shifts our understanding of the Milky Way from a passive spiral galaxy to one with a dynamic and episodically active center. It also speaks to the resilience of matter under extreme conditions. The hydrogen clouds not only survive being transported to high latitudes, but have persisted in a plasma-dominated region for millions of years. Understanding how they manage this could refine models of cloud stability, erosion, and magnetic confinement. Their presence also connects to broader ideas about galactic feedback, the way black holes influence their host galaxies. Energy expelled from the core can heat gas, suppress star formation, or in some cases, displace and recycle cold material across the galaxy. This means the Fermi bubbles may not just be destructive. They could recycle material for future star formation. The discovery of cold gas alongside hot gas reveals a multi-phase structure, adding new depth to how we understand these massive features. This discovery doesn't just date a black hole eruption. It reveals how such events can shape galaxies for millions of years. It also highlights the power of multi-wavelength data with radio, gamma, and X-ray observations together, uncovering a deeper, more complex galactic story. Now that these cold clouds have been identified, the next step is to look for more of them. So far, the 11 detected clouds are all located in the northern Fermi bubble. There's still no clear data on whether similar clouds exist in the southern bubble. A larger survey using radio telescopes could provide a more complete map and help determine whether the phenomenon is symmetrical, something that would support the idea of a bipolar eruption from the galactic center. Understanding how the clouds formed and survived will also require more detailed observations. Are they magnetically shielded? Are they moving differently from the hot gas? Do they contain trace elements or molecules that give clues about their origin? Another key question is whether the clouds were pulled from the galactic disk or formed in place from cooling plasma. If they were lifted during the eruption, they could be fragments of larger clouds or star-forming regions that were disrupted. If they formed locally, it would imply that hot gas can condense in certain conditions, something not well supported by current models. Tracking the cloud's motion could reveal how violent the bubble's origin was. Fast-moving clouds suggest an explosive event, while slower ones hint at gradual winds. And with Sagittarius A** still flaring, another eruption might not be as distant as we think. This discovery reinforces a key idea. Even galaxies like the Milky Way face internal disruptions. It shows how core activity shapes gas flow and star formation. With tools like SKA, JWST, and new X-ray telescopes, we're set to uncover even more about our galaxy's dynamic nature. Cold hydrogen clouds inside the Fermi bubbles are rewriting what we thought possible, surviving in extreme heat, and pointing to a recent eruption from our galaxy's central black hole. These clouds aren't outliers. They're clues to how galaxies evolve. The Milky Way's core isn't as quiet as we thought. Stay tuned. This story is just heating up. Astronomers have discovered cold hydrogen clouds inside the Milky Way's scorching Fermi bubbles, something once thought impossible. This surprising finding hints that the powerful explosion behind the formation of these bubbles, likely triggered by a violent event at the galaxy's central supermassive black hole, Sagittarius A**, may have occurred much more recently than previously believed. It's a game-changer for how we understand galactic evolution and black hole activity. In this video, we'll break down the discovery, how it was observed, and what it means for our broader understanding of the cosmos, from the structure of galaxies to the violent dynamics at their cores. The Fermi bubbles are vast lobes of high-energy plasma that stretch tens of thousands of light-years above and below the galactic plane. First identified in 2010 using NASA's Fermi Gamma-ray Space Telescope, these immense structures are invisible in visible light, but shine brilliantly in gamma-ray and X-ray observations. Scientists had long believed that the bubbles were relics of a powerful outburst, perhaps a blast of radiation and matter caused by intense accretion activity from Sagittarius A** millions of years ago. Until now, these bubbles were considered regions of purely hot, turbulent plasma, an environment inhospitable to the delicate structure of cold gas clouds. That's why the discovery of cold hydrogen clouds nestled deep inside these hot plasma regions is so unexpected and so revolutionary. It's the cosmic equivalent of finding snowballs inside a volcano. Led by Rangman Bordeloi and a team at North Carolina State University, the researchers used the Green Bank Telescope in West Virginia, one of the world's most sensitive radio telescopes, to detect these clouds. Ranging in size from 13 to 91 light-years across, the clouds were discovered some 13,000 light-years above the galactic plane, within the northern Fermi bubble. What makes these clouds remarkable isn't just their location, but their temperature. Though termed cold, the hydrogen gas registers at around 10,000 Kelvin, cool relative to the million-degree plasma surrounding them. Under normal astrophysical conditions, such clouds should be unstable and short-lived in such a hostile environment. They should have been torn apart, ionized, or evaporated long ago. The fact that they're still intact tells us something profound. They were likely swept up during the initial eruption that created the Fermi bubbles and have managed to persist since then. This offers us a rare cosmic timestamp. If the clouds are slowly eroding due to their surroundings, as models suggest, then their survival implies they must have been introduced into the bubbles relatively recently. Otherwise, they wouldn't still be visible. This discovery thus acts like a galactic clock, suggesting that the massive eruption that formed the Fermi bubbles occurred just 6 to 9 million years ago, far younger than some previous estimates, which ranged up to 30 million years. This updated timeline has dramatic implications. It tightens the estimated window for the Milky Way's last significant central outburst. Instead of being an ancient remnant of a distant past, the event that created the Fermi bubbles now appears to be a relatively recent episode in galactic terms. It hints that Sagittarius A*, the dormant-looking black hole at the center of our galaxy, was highly active in the not-so-distant past. This challenges long-held assumptions about the Milky Way being a passive spiral galaxy with a quiet center. In fact, it now seems that our galaxy has a far more dynamic and volatile core than previously thought. The cold hydrogen clouds also highlight the incredible resilience of matter under extreme conditions. These clouds not only survive being violently displaced from the galactic disk, but have also endured the searing plasma conditions of the Fermi bubbles for millions of years. Understanding how this is possible could lead to refinements in our models of cloud stability, erosion, magnetic confinement, and the thermodynamics of interstellar matter. Moreover, these clouds provide new insights into galactic feedback, the complex process by which energy from a central black hole influences its host galaxy. Traditionally, feedback from black holes was thought to be mainly destructive, heating up gas, preventing star formation, and blowing material out of the galaxy. But the discovery of cold hydrogen clouds in a region dominated by hot gas suggests a more nuanced picture. It implies that feedback can also be constructive, recycling material, compressing gas, and possibly even triggering new star formation in some cases. In this light, the Fermi bubbles may not be mere scars of past violence, but active participants in galactic regeneration. The coexistence of hot plasma and cold gas reveals a multi-phase structure, different states of matter living side by side, adding new complexity to how we understand massive galactic features. This multi-phase nature is crucial for explaining not just how galaxies evolve, but also how they sustain themselves, form stars, and interact with their environments. The discovery also emphasizes the power of multi-wavelength astronomy. These cold clouds remained hidden in optical and infrared surveys. Only by combining radio observations from Green Bank with gamma-ray and X-ray data from Fermi and other observatories were scientists able to uncover the full picture. This synergy between instruments underscores how different wavelengths unlock different layers of the universe's story, revealing structures and dynamics invisible to our eyes alone. Now that these cold clouds have been identified, the logical next step is to look for more of them. So far, the 11 clouds detected are all located in the northern Fermi bubble. It remains unclear whether similar structures exist in the southern counterpart. A more comprehensive survey using radio telescopes like the upcoming Square Kilometre Array, SKA, could help map the full extent of this phenomenon. If symmetrical cold clouds are found in the southern bubble, it would lend strong support to the idea of a bipolar eruption from the galactic center, one that blasted material in both directions millions of years ago. But many questions remain. Are these clouds magnetically shielded? Do they move differently than the surrounding plasma? Are they chemically distinct, perhaps carrying trace molecules or elements that provide clues about their origin? Crucially, were these clouds pulled from the galactic disk during the eruption, or did they condense locally from the hot gas? An idea that challenges existing astrophysical models? If the clouds were lifted from the galactic plane, they could be remnants of star-forming regions disrupted during the explosion. If they formed in place, then we must reconsider how cooling works in hot plasma environments. Understanding their motion could also offer key insights. Fast-moving clouds would indicate a violent, energetic eruption, while slower, drifting ones might suggest a more gradual wind or fountain-like outflow. Observations of their trajectories could even be used to reconstruct the dynamics of the original explosion, like tracing the fragments of a shattered object to determine the force that broke it. And this discovery arrives at an exciting moment. With Sagittarius A** still exhibiting periodic X-ray flares, it's entirely possible that another central outburst may be brewing. If another eruption occurs, it could reshape parts of the Milky Way once again, offering scientists a front-row seat to one of the universe's most energetic phenomena. We're no longer looking at a galaxy that has settled into a calm adulthood. Instead, we see a living, breathing, sometimes volatile system, capable of dramatic transformations. This finding reaffirms a central truth about astronomy. Even familiar places can still surprise us. The Milky Way, our cosmic home, still harbors mysteries that challenge our assumptions. Cold hydrogen clouds inside the Fermi bubbles are rewriting what we thought was possible, surviving in intense heat, pointing to recent black hole activity and hinting at the processes that drive galactic life cycles. These clouds aren't anomalies. They're messages from the past, traces of cosmic events that continue to echo through time. Their presence reveals that our galaxy's story is not static, but dynamic and evolving. It forces us to reconsider not just when the Fermi bubbles formed, but how matter behaves under extremes of temperature, pressure, and radiation. With advanced tools like the James Webb Space Telescope, SKA, and next-generation X-ray observatories coming online, astronomers are poised to dig even deeper. They'll probe the molecular composition of these clouds, study their motion in detail, and uncover whether similar phenomena are present in other galaxies. The Fermi bubbles are no longer just silent remnants. They're active players in our ongoing quest to understand the universe. And in all of this, the cold hydrogen clouds are no longer just clouds. They're keys to unlocking a deeper, more complex, and more thrilling picture of the Milky Way's past, present, and future. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.